Okay, we're in our 5th video. This is the last video in chapter 13. We're looking at properties of liquids. We just talked about intermolecular forces of attraction between different particles, and we said the highest intermolecular force of attraction that you have, the strongest, is hydrogen bonding. And water is a hydrogen bonding compound. So we talked about why water had such high boiling points, because of those strong intermolecular forces of attraction. So while we're talking about water, we're going to move over to hydrates. What is a hydrate? Well, a hydrate is a solid that contains water molecules as a part of the crystalline lattice structure. So an example of what a hydrate is would be a compound written like this in its formula form. If we removed the water from this formula for a second, we would read that this was calcium chloride, right? It was an ionic salt. So you know there's cations. For every one calcium plus 2 cation, there's 2 chloride minus 1 anions in that salt. However, if we see a dot, so here I'm going to blow that up. We've got CaCl2. This is known as an anhydrous salt. Anhydrous salt. Anhydrous means without water. So this would be a salt that didn't contain water in it. Whenever there's water that's included or trapped into the crystalline lattice of a solid, we call that the hydrate form of the salt because it's been hydrated with water. A hydrate is always written in a chemical formula by showing a dot next to the anhydrous salt. So next to that, once we have water bound to it, this is called the water of hydration. Water that's loosely bound inside of the crystalline lattice. So here we have the dihydrate, or there's 2 waters bound to every 1 calcium chloride salt unit in the system. It's a stoichiometric formula unit that's made. This entire thing, the anhydrous salt formula plus the water of hydration, the number of waters present per structural unit, that entire formula there is called the hydrate. That is called the hydrate. And I know once again that a formula is of a hydrate if there's a dot bonding the waters. That dot means loosely bound inside of the crystalline lattice. So what is the water of hydration? Those are the water molecules that are loosely bound into the crystalline lattice, which means that those water molecules are not tightly bound. They can actually be removed through heating. So one thing we can do is we can decompose the hydrates. That is, we can remove the water or break the water apart from the salt, and we can get the anhydrous salt out. So we'll talk about that in a second. First of all, let's talk about how we're going to name hydrates. If you're given a formula of a hydrate, how do you name it? Well, remember we said there's always the anhydrous salts, the ionic salts. We know how to name those already. You can study how to name ionic compounds going back to chapter 6. So you're always going to name the salt first, but at the end of the salt's name, calcium chloride, sodium hydride, or, I don't know, copper 2 sulfate. After that, you're going to name the hydrate of the salt. So you're going to call it a hydrate. Now, some salts can have multiple hydrates. Copper 2 sulfate is one example. It can be a heptahydrate, a septahydrate, a dodecahydrate. So the number of waters that's bound to the salt needs to be indicated because you can have different types of hydrates, different numbers of water bound. So you're going to use a prefix, the same prefixes we used in chapter 6 for molecules: mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. We're going to use those same prefixes to tell how many hydrates are bound. So for example, when we have CaCl2, 2H2O, the name of that hydrate is calcium chloride, but since there's two waters, it's the dihydrate. So we name the prefix hydrate. All right, what about the next one? FeCl3 dot 6H2O. All right, so we're going to name the salt first. Now, this is an iron chloride salt, but remember, iron can have two different charges. It can be +2 or it can be +3. Because chloride's -1, there's 3 of those, so -3 charge total. There's only one iron, so it must be iron 3. So this is the iron 3 chloride salt. Once again, if you don't know how to do that, go back and review chapter 6, okay? So this is iron 3 chloride. And then we've got 6 waters loosely bound, so this is the hexahydrate. Alright, so that's how you name the hydrates. Not hard at all. Let's talk about how you could decompose the hydrates. If you've got water loosely bound in your crystalline lattice, you can just heat it up to remove the water. So heating the hydrate will remove the water. For example, here we have copper 2 sulfate pentahydrate. I've shown a chemical reaction here at 250 degrees Celsius, so adding heat to decompose into 2 different compounds. Remember, decomposition breaks down into smaller individual pieces. So here we have the individual hydrate. It's going to break down into the anhydrous salts plus 5 waters. All right? So the water can be completely removed by heating. What we can do is we can calculate by the change in the mass of the salts, because when the water is removed from the salt, water will be very hot. It will be the gaseous form. So that water can evaporate away. Imagine you have a crystalline solid inside of a crucible here. So this is the hydrate. If it has a certain mass with the water and the salt combined, once the sample or the crucible is heated, let's say there's some water loosely bound, if that water evaporates after heating, you've lost some mass. So those 2 waters are evaporated, and now you only have the anhydrous salt left. You've lost mass through the heating. The change in the mass, so you've got the mass of the water, and you've got the mass of the salts still inside of your crucible. The change in the mass can tell you what hydrate you have. So what we're going to do, we're going to do some problems where we figure out what the percent water in a hydrate is. By looking at the formula, we can calculate that. Or, and from that information, if we calculated the percent water by mass lost in the lab, we can determine which hydrate we have. So let's practice, if we're given a formula, how to calculate the percent mass that we should expect of water lost should that hydrate be heated. So when you calculate the percent of any part of a compound, even if it's a hydrate, you're always going to calculate the percent by mass. So the mass percent, or the percent of anything, by the way, is always part over the whole. So when you calculate the mass percent, or the percent water, percent mass of water in a hydrate, you're going to divide the mass of the water divided by the mass of the entire hydrate, the part over the whole, times 100%. Okay, now, the mass of the water, that's just the grams of the water in the formula. And we're going to use the grams on the periodic table to calculate this. The mass of the hydrate will be the grams of the salt in the equation plus the grams of the water. So it's the part over the whole. It's not the water divided by the salt. It's the water divided by the mass of the salt plus the mass of the water, the entire thing times 100. So let's practice calculating, the mass percents of water in each of these hydrates below. It says calculate the mass percent of water in copper 2 sulfate pentahydrate. Okay, we're going to look at the periodic table here when we solve for this. So it says, so right now we've got copper 2 sulfate pentahydrate. If we want to know the mass percent of water, the percent of anything is always the grams of that thing divided by the part over the grams of the entire thing. So we're going to calculate the grams of water in that formula divided by the grams of the entire hydrate. Copper 2 sulfate pentahydrate. Okay, a few things to mention here, because I'm not going to do, it's painful if I came here and showed you every step. I know that you know how to calculate the mass from the periodic table. So assume that you have 1 mole of compound. If you have 1 mole of this compound, you can use the molar mass from the periodic table and sum things up. So the molar mass of hydrogen, for instance, if we want to know the mass of water in the compound, well, the molar mass of hydrogen is 1.01 grams per mole. But how many hydrogens do we have in the water? We have 5 waters. Okay, so 1 hydrogen is 1.01 grams. But we have 5 times 2 of them. We have 10. So the total mass of hydrogen is 10.1 grams in the compound. Likewise for oxygen, oxygen's 16 grams, but we have 5 of them. So 16 times 5. So the total mass of water will be 5 waters. Water, by the way, is 18.02. You could also do it that way. 1 molecule of water is 2.02 plus 16.02. So you could say that 1 molecule of water is 18.02 grams per mole from the periodic table. So 5 times the molecular weight of water, which is 18.02, 18.02 times 5 waters is 90.10 grams of water in that entire hydrate. Now we're going to divide that by the mass of the entire hydrate. We've already got the mass of the water. It was 90.01 grams. Or 90.10 grams. Now we need to include the mass of the salts, copper 2 sulfate. So you've got 1 copper, 1 sulfur, 4 oxygens. Alright, so how much does the anhydrous salt weigh? It weighs, and I did this earlier, I'm not going to lie, 159.62 grams. Okay, so that came from the periodic table as well. It's the molar mass of the salt plus the molar mass of the water. So overall, my percent water is going to be 90.10 divided by the sum of the salt plus the water times 100. I get 36.08% water by mass in the hydrate. Now, why is that important? Okay, if you go in the lab and you suspect that you have copper 2 sulfate hydrate, some hydrate, it could be the heptahydrate, the pentahydrate, the monohydrate, you don't know what it is. If you suspect it's the pentahydrate, meaning 5 waters bound, then you're going to do a mass calculation. You're going to take the mass of the original compound. You're going to decompose by burning off the water in a crucible. Then you're going to weigh the final salt that's anhydrous. You should have lost by mass 36.08% water, and that would confirm that you had the theoretical percent yield, the pentahydrate. So we use this in the lab. We calculate what the pentahydrates percent water should be, and then we confirm it in the lab, and we can identify the hydrates by this method, how many waters are bound in the salt. All right, so let's do one more here, if I can. It's mad at me. There we go. So it says, there's another one here on the bottom. So just get used to calculating percent mass of a water in a hydrate from the formula. The second one says, what mass of water in grams is found in 1 mole of barium hydroxide octahydrate? Okay, so here we're actually not asked to calculate the percent water, but we're asked to calculate the grams. You can do this one for yourself, but basically I just want to get you started. It says you have 1 mole of barium hydroxide octahydrate. Well, barium on the periodic table is Ba, and it has a +2 charge. You're going to have to write this compound down correctly. So barium is Ba2+. We know that hydroxide is OH-. So if we have a -1 and a +2, we need 2 hydroxides for every 1 barium. We've got to balance the charges in that formula. Once we do that, we say, what now? That's balanced. That's the anhydrous salt, but we have the hydrate. It says octahydrate, so we have 8 waters here. All right, so this question says, what is the mass of water in grams in 1 mole of barium hydroxide octahydrate? So if we assume we have 1 mole of this compound, there are 8 moles of water for every 1 mole of the hydrate. If we know that water weighs 18.02 grams for every 1 mole, if we have 8 moles of water bound, then that's the number of grams, and I don't have that on me, but that's the number of grams of water that's bound. All right, so depending on the question you're asked, you might be tested over calculating the percent mass of the water, so the grams of the water divided by the grams of the hydrate, or I might ask you to give me the formula of the hydrate if I give you the name, so know how to name the hydrate. And I might ask you to combine all of that together. I might give you the name and ask you to find the percent water in the hydrate. We'll be doing this in lab in a few weeks, but go ahead and practice the problems, and you'll see there's practice on your homework too. Do not forget to do your homework. It's very, very important that you always do your homework and practice these problems. A lot of the problems that we go over, either on the homework or in your book when you're reading, or if you're watching the lectures, are very similar to the problems that appear on the test. So just keep studying. We're getting near the end of the semester here, so just keep going. You're doing good. All right? Have a good week.